Okay, so we need to talk about functions of two variables. Okay, so first things first, I just want to talk about functions for a second. And this is the exact same lecture that Algebra 2 students get. So I'm assuming that you guys are familiar with this concept. So hopefully you all can supply most of the information here. So what's a function?
The relationship between
something that works.
given outputs.
Okay, so I'm going to give you guys maybe a more serious definition. So, what the hell, I'll give you the same. So a function is a rule, right, associating inputs to outputs with each input associated to one and only one, oops, that's not how you spell only, output. Cool? Okay. This thing, this with each input associated to one and only one output, right? That seems like extra.
It's not.
That's like more than what Chris said, right?
Yeah, it is.
So why does that have to be in there?
Because sometimes there are multiple versions of inputs to correlate the same sort of output. Or I don't.
Otherwise, it's just like a picture.
Oh my gosh, multiple outputs.
It's just a relationship.
Yeah, so there's a thing called a relation, which is a function except that it doesn't have this chunk. So a relation is just a rule associating inputs to outputs. That thing doesn't have to be predictable. It can be a gumball machine. Okay? I want to get the difference in your head here. A function is like a paint booth. Right? Like, and assume that our paint booth only has one color.
Oh.
So you put something in the paint booth and all it does is paint the thing blue. Right?
Okay.
So we have the blue paint booth. Whatever you put into it, it's going to paint it blue, and that's all it's going to do. You guys see that? A gumball machine is not a function. Where you put a quarter in and who knows what you get? Right? That's a relation, not a function. A function has the very nice property that every time you hand it an input, it gives you the same output. Cool?
Like a vending machine. Right?
No.
D7, you get one.
Oh, yeah, sure. Like the coordinates on a vending machine, right?
Yeah, like
so you push D7, you always get M&Ms.
Yeah.
Assuming the vending machine's working properly.
In an ideal world, right, D7 always gives you M&Ms. Cool?
Not ideal world.
So that's actually a nice example of a two-dimensional function. You guys see that? It takes two inputs, a letter and a number, and gives you some kind of output. I want to drive home that what we're doing is not actually new, it's just a little different. Right? So functions still mean the same thing. The picture that goes with a function, do you guys know bubble diagrams? If I made any?
It's
Some.
if you show it, yeah.
So a bubble diagram is just this thing.
Oh, yeah.
This is a function, right? It takes stuff over here and turns it into stuff over there. These are the inputs, right? What's the other name for all the available inputs?
Domain.
Good. The domain is all the inputs that work. You guys see that?
Yeah.
So in my blue paint booth example, what's something that's in the domain?
The object you're putting in the booth.
Yeah, some kind of object that I can fit in the booth. What's something that's not in the domain? Yeah, something that doesn't fit in the booth is a great example of something that can't go in the paint booth. You guys see that? Like, I don't know, tamarack. Tamarack probably won't fit in the paint booth because it's enormous. Right?
Unless
You
it's
see that?
industrial
It's
size.
bolted to the ground, too.
Yeah.
Cool. It's only as bolted down as you can't cut it. Okay, so inputs make the domain, right? Those are the things that are going to go in the function. What's the stuff that comes out?
The blue version of what our input was.
Yeah, good. So in the paint booth example, right, that's just blue stuff, right? So that's the outputs,
Or range.
and that's the range. Okay, now, I just broke that. Somebody's gonna, one of you guys want to scan that? 3D print a new one? Seriously though, if someone wants to do that, that would be great. Keep in mind the range is not necessarily all of the kind of thing you were aiming at. Right, so the blue paint booth paints stuff, right? The only stuff you're going to get out of the blue paint booth is blue painted stuff. You guys see that? Oh shit, my car's blue. My wife's truck is white, and so it is not in the range of the blue paint booth. You guys all see that? Right? Although it's a painted thing, it's not hit by the blue paint booth function. You guys see that? So this gets a little tough in the linear algebra land. There's something that distinguishes between a range and a codomain. The codomain is like the category of stuff you were aiming at, and the range is just the stuff you actually hit. You guys see that? So keep in mind here, a range is the stuff you're actually hitting. It doesn't matter which thing you hit it with, you just have to hit it with something. You guys want another kind of stupid example of a function, or are you okay? Good? Okay. All right. I'm not going to give you the definitions of domain and range. I'm assuming you've seen those before. Should I say them quick anyway? Okay. So the domain is the set of all the possible inputs, and the range is the set of all the outputs that are actually mapped to by an input. Cool? It doesn't, also keep in mind, the range doesn't have to be a lot of stuff. Right? The range can be one thing, or no things in the odd case of what we call the empty function, which is the function that doesn't take any inputs and doesn't give any outputs.
Like an empty set.
Yeah, stay away from that one, it's weird. The empty function is just a function between the empty set and itself.
Oh, God.
Don't worry about it. One function that does make a lot of sense, that has a really small range, is the one that just takes whatever you gave it, throws it away, and gives you the same thing every time. Okay?
The function is multiplied by 0.
Exactly. So the crush function, right? The one that just takes whatever you gave it and gives you 0 back, multiplied by 0, right? That's a function where the range is pretty small. The domain's pretty big, right? The range is extremely small. You guys with me on that? Okay. All right, cool. So here, right, in 18C land, we are going to talk a lot about functions of 2 variables. Okay? And so here, usually I'll tend to assume that input type things are points. You can think 2D at points, right? And outputs are usually, are also assumed to be numbers, like maybe numbers in font. Is this symbol tweaking any of you out? You guys seen these symbols before? Yeah. Anybody not seen symbols? Yeah. So these would be, outputs are assumed to be numbers, i.e. in the real numbers. They don't have to be, but that's the category we're usually going to operate in. Okay?
You said the inputs are 2D, that means the outputs are 3D, or are they also...
Outputs are 1D. So this is a 2 thing to a 1 thing, so to draw a picture, I need 3. right? I need 2 inputs and an output. Can you guys give me an example of a nice 2D to 1D function?
A squared plus B squared equals C squared? No. Because it changes line.
So we could do something like this, right? We could write C of A and B, right? You guys all with me on this? Like this is the function's name is C, it takes inputs A and B. And we could do something like A squared plus B squared and then square root the whole mass. You guys see this? What does this thing calculate? This is the length of a hypotenuse with sides A and B, right?
Yep.
It has to be a right triangle.
Good, thank you. Right triangle with sides A and B.
So if X dimension, Y dimension makes a straight line. That's why I was thinking 2 dimension to 1 dimension.
Yeah, actually a better name for this would be the radius. Okay. This is just how far A and B are from 0. Do you guys recognize this formula from polar? Right, like if I wrote this as R of X and Y is the square root of X squared plus Y squared.
Yeah, of course.
Right, this is just how you take an XY point and turn it into a radius. You guys recognize that one? So you know some examples here, like there's one. You guys should also know something theta of X and Y. How do you get the angle out of a point XY?
Inverse tangent.
Good.
Of
So this is arctangent of,
y over x.
so I think it's y over x too. How can we check our reasoning?
Well, it's just basically the arctangent of the slope.
Yeah. Don't get fancy. We're looking for theta, right? Y is the one that goes up. X is the one that goes over. Let's see. And tangent is the opposite over adjacent. Good trigger view. So y over x, and I want to undo the tangent function, so I want arctangent of that. Cool. There, look. You already knew 2 of these. Easy. Chill. Right? Okay, now, what does the graph of this one look like?
You'd have to parameterize it to use it.
Damn.
Look at the circle.
Okay.
What is it?
Okay, wait, let's try an easier one. All right. Hang on, let me turn this thing. Okay, so we're going to do one dumber. We're going to try graph
Equals x squared.
f of x and y is x squared plus y squared.
That's the circle,
Well, that's the same.
right?
Okay, you're going to have to forget some stuff.
Oh,
The thing you're going to have to forget is some of these relationships where they're equal to a constant. Right? Because x squared plus y squared equals 4 is a circle. Right? Usually there's a radius squared on the other side of this thing. And here I have f. Right? So this isn't a shape.
it's a domain.
Right? This is a function. It takes x's and y's, and the way it does that is by doing this. Right? It takes the x coordinate and squares it, adds it to the y coordinate squared. So I need to figure out what this thing looks like.
Kind of looks like a plane, doesn't it? That just like shopping through.
Nope. So, frankly, I am too dumb to do this well without some assistance. So what we're going to do is we're going to do the exact same thing for every surface we run into right at first. We are going to slice it up. So you guys recognize that 4 equals x squared plus y squared is what? Circle, radius 2, right? Okay, so I'm going to go like this. I'm going to go, all right, here's x, here's y, z is sticking out at me, right? You guys all see that? So I'm going to go out to a radius of 2. I'm going to draw my circle around here, and I'm going to write on that thing z equals 4. Why did I do that?
Oh, because the height is 4. Where the circle
Yeah,
is.
so I set the output, right, the z variable equal to 4, and then I said, okay, that's this shape. Well, this shape's a circle. So when the output's 4, that happens on this circle.
This is a cylinder, isn't it?
No,
It's a cone.
no,
Well, that's weird stuff.
kids are getting there. Okay, so how can I get another one? Like this is one level. Do you guys see what I did? I have some 3D shape, I don't know what,
Oh,
and I just sliced it.
this is a 2D object in the end?
This is a 3D
The
object.
cutout of the cone inside is everything else of the cone, or the cone that is box.
So what I did was I have this surface, right? One of those draped handkerchiefs, and I cut it at z is 4. You guys see that? I hard coded the output to 4. And then I kind of looked at that and I found that's a circle. So let me hard code the output to something else. Like 1, say. Okay, so when 1 is x squared plus y squared, what's that look like? A circle of radius 1.
Oh, is it just like?
So that z is 1.
Is it just a plane that kind of goes off to?
So that's what I'm slicing with, right? I'm slicing with a horizontal plane, and I'm looking at what's left. You guys see that? Really, I'm just saying, if I told the 3D printer to make this, right, where would it be running at height 4? Where would it be running at height 1? Where would it be running at height 0?
So it's putting a half sphere then?
Not quite. Where would it be at height 0?
Well,
The
x and y
origin.
would have to be 0, so it's
Yeah,
just the origin.
right? If x squared plus y squared is 0, that means both x and y have to be 0.
On this thing.
So that would be here. That z is 0.
Oh, it's going.
You guys see what I'm making here? I'm making a topographic map, right?
So it's like a colander?
Kinda.
Isn't like going
Getting
very
closer
low?
with the colander and the half sphere.
Isn't it like a parabola? But just
Oh, yeah.
Good, yeah, this is a parabola spun around in a circle.
Oh, gosh.
You guys all see that?
Yeah, I remember.
Because this gives out, right? When I put a point in here, I get the radius squared. So as I move along, the radius goes up like squaring. And so I get this kind of parabola spun around, right? You guys see that? And the origin's down here, and I have x and y and z. You guys with me on this? Okay, so the next thing we're going to do a bunch is contour mapping. Okay, so we're going to slice a bunch of stuff with contours, and we're going to look at how to make shapes out of those things. Cool? So when we come Wednesday, we're going to go walk around, and we're going to look at contour maps on the ground, like with ribbon or paint or something. And then we're going to stand over them and see what they look like so we can get a feel for terrain versus contour maps. Cool? All right. If you have some time, go flip on terrain view on Google Maps and go look at someplace you know about. Like go look at campus, or go look at the area around your house, or go look at, I don't know, whatever place you walked last up Sonora Pass. Like you went to Pinecrest this summer, like flip open the topo map for Pinecrest and just look at it, see if you can figure out what's going on. Cool? All right, I don't have time to give you a quiz, so we'll give you a quiz later.